afternoon and welcome to the BrainLink X Lab Day Talk Concert. My name is Ki-Hoon Kim. I'm your moderator today. I'm working at Seoul National University and Department of Physics. I welcome you all for today's event. So the phenomenon of superconductivity and its applications has become an important scientific topic that many people in South Korea are currently following with interest. Superconductors are a representative example of quantum materials. Therefore, we would like to try to understand the phenomena occurring in the broader field of quantum materials related to superconductivity and make predictions for the future. Therefore, today, we will gather 6 world-renowned scholars from the United States, China, Germany, and Korea to give a talk concert on the topic of quantum materials and phenomena related to superconductivity for about 2 hours. So first of all, let's have a short video introducing the BrainLink program.
Amidst the world's rapidly accelerating changes and competition, what kind of future are you preparing for? We are chartering a path to the future through science and technology exchanges, bolstered by international cooperation. In this era, where scientific and technological competitiveness is directly linked to a nation's diplomacy and security, the power to overcome such challenges lies in international cooperation that fosters synergy through collective efforts, and from talents who will shape the forthcoming era. The scholars of the world are gathering in Korea. A platform that facilitates exchanges between Korean and international scholars, as well as between seasoned and emerging researchers, is taking shape. BrainLink X Lab Day, organized by the Korean Federation of Science and Technology Societies, aims to be a global hub of talent. By consistently enhancing and expanding the global talent network, we're laying the groundwork for a brighter future. By inviting global scholars, X Lab Day provides an opportunity for young Korean researchers to glean insights from the vast knowledge and experience of both Korean and international scholars, as well as to engage in collaborative research. In 2022, the inaugural X Lab Day saw a total of 14 meetings across various technical fields. Altogether, 449 individuals participated, comprising 70 from overseas and 379 from Korea, all aiming to build a stronger network in Korea and abroad. This year, for our 2023 X Lab Day, we have the honor of having Xingteng Yao, professor at Tsinghua University and a Fields Medal winner, Philip Kim, a globally renowned professor at Harvard University, known for his research in graphene, Yun-Sung Hwang, professor at Stanford University and Hoam Award winner, and Humboldt Research Award winner, Zhigang Suo, professor at Harvard University, leading discourses of their respected fields. This year, the discussions will span 12 national strategic technology fields pivotal to Korea's advancement, including quantum mechanics, nuclear technology, and AI. The event will see the participation of 30 Korean and international scientists and engineers. With 2 organizers leading each technical segment, the gathering will foster in-depth academic exchanges, encompassing the sharing of recent trends and information in core technology fields, in-depth discussions on research findings, and the sharing of ideas. The focus of X Lab Day is connectivity and sustainability. Following the event, communities and clubs will be established based on each X Lab Day session to ensure ongoing dialogue among attendees and promote collaborative research. To ensure that today's dialogue becomes the seed for tomorrow's magnificent achievements in scientific and technological development, COAST supports the reinforcement and expansion of the networks established through XLab Day. COAST, the organizer of XLab Day, stands as a beacon for Korea's science and technology society. Established in 1966, its mission has been to safeguard and amplify the rights and interests of scientists and engineers. Our endeavors extend to enhancing the public's grasp of science and technology and furthering its development through comprehensive policy research, planning, surveys, and consultations. As Korea's largest science and technology network with over 600 affiliated organizations, we are committed to promoting domestic and international cooperation and exchange. In the transformative era of the Fourth Industrial Revolution, where science and technology spearhead groundbreaking challenges, COAST remains dedicated to its role as a facilitator of scientific and technological innovations. In this era of technological dominance, we will navigate through the fierce competition by fostering global cooperation in the fields of science and technology. BrainLink XLab Day aims to broaden both domestic and international talent networks and become a global hub of talent. By making XLab Day into an event that scientists and engineers worldwide eagerly join, we intend to elevate Korea's global standing and bolster national competitiveness. Global Talent Hub, BrainLink XLab Day.
Okay, great. It's my great honor to introduce our first speaker. So we allow here great speech from 6 scholars, and the first speaker will be Professor Piers Coleman, who is now currently at Rutgers University, United States. As a leading scientist in heavy formation superconductivity and theory of superconductivity, he has done numerous great jobs in physics. He's actually a 2000 APS fellow and 1990 in IOP UK fellow. And today he will talk on general aspect of superconductivity. So let's welcome Piers Coleman.
Well, thank you for inviting me, Ki-hung. It's a great pleasure to be here. I've never attended any of your BrainLink events, but they look very exciting. I'm a co-director of the organization ICAM, the International Institute for Complex Adaptive Matter, and I hope that this will be an occasion for us to link up and actually do some collaborative activity in the future. But what I'm here today to talk to you about and to engage in a discussion today is the materials challenge of the quantum. Can you hear? I'm not doing anything. I'm just talking. Okay. So this is a very quick outline of my 10-minute talk. And before I start, I wanted to remind you about the fact, about the deep link between the laboratory and the cosmos. We are at the beginning of the 21st century, but we are part of an adventure in science that stretches back to the beginning of the Renaissance. And at that time, early physicists discovered that by looking at the cosmos, they could learn about the world they live in, and that by looking at the world they live in, they could understand about the cosmos. And this is something that began with Galileo and Newton in the 1600s, continued in the 20th century with work such as the work by Anderson and Higgs, who understood from the properties of superconductors how to understand the breaking of the symmetry between the electric and the weak force. And this opportunity to learn about the cosmos and to learn about the world we live in continues today, and a deep potential for fundamental discovery is alive with us today, and it's very important that we understand this motivating philosophy. So moving along, what we're really talking about today is quantum mechanics. There's a delightful creak in the floor here. Every time I move, you get a creak, but never mind. And it's distracting for me, though. Any way I can take a mic with me somewhere? How about here? No escape. Okay, so 2024 is the 100th anniversary of Louis de Broglie's hypothesis that electrons are matter waves. And around 100 years ago, a young man in Paris was putting together his thesis, a thesis that was so controversial that the French sent it away to Germany for Einstein to review. And his conclusion was, it makes a lot of sense. And so we're here today to discuss this continuing revolution and one of its most remarkable manifestations, superconductivity and quantum materials. And you may think that 100 years ago is a long time, but in scientific revolutions, 100 years is a short time. Classical mechanics took more than 200 years from its inception to the discovery of energy, and quantum mechanics is a young field at the age of 100, and there are fundamental discoveries and fundamental technologies yet to be discovered. Okay? So we're not in after it's all happened, we're in right at the middle today. Okay? And so let me tell you a bit about this old history, though. Here's a picture of de Broglie and Davis and Germer. De Broglie, in 1924, proposed his thesis that electrons are waves. And his idea allowed the structure of the atom, and in particular Niels Bohr's picture of the atom, to be understood in terms of electron waves. But it unleashed a new idea. The idea that electrons are waves led to a wave equation and a completely new structure of understanding of matter at the microscopic level. Here is a picture of Davison and Germer, who were working for the industrial lab, Bell Laboratories, in the heart of New York City. And later that year, they discovered the evidence for electron diffraction, proof that electrons are waves. And just 1 year later, 1925, next year will be the 100th anniversary of Heisenberg and Schrödinger. They, together with several others, went on to formulate the mathematical framework of quantum mechanics. In fact, between 1926 and 1933, the entire construction was put together. With this, and of course, one of the key ideas was the idea that electrons are probability waves. Okay? And this enabled physicists to understand magnetism, to understand the behavior of electrons in matter, and it led to Dirac's prediction of antimatter. Although you may be wondering why I put Oppenheimer up there, he was one of the people who convinced Dirac that the antiparticle to the electron was not the proton, but must be an independent particle. But remarkably, the topic of today's discussion, superconductivity, remained unsolved until 1957. One of the important ideas to emerge from these early days of quantum mechanics, which played an essential role in our understanding of superconductivity, was the idea of coherence, which has its origins in the work of Bose and Einstein in 1924 and 1925. One of the important ideas to emerge was the idea of coherence. Okay? And in fact, Bose wrote a letter to Einstein from Calcutta showing his new work. Einstein had it translated into German and was published in Germany, and he then extended Bose's idea. Okay? And so their names are forever connected in the word Bose-Einstein. So here's the idea. On cooling, Einstein predicted that bosons would coherently superpose into a single quantum state, a Bose-Einstein condensate. So that on cooling, starting at high temperatures, the de Broglie waves would be incoherent. But as you cool them down, they would all drop into a single coherent state, and we call that a condensate, a quantum condensate. And this idea is fundamental for our understanding of many coherent quantum phenomena. It explains lasers. It explains superfluids, both atomic and, for example, superfluid helium-4. And it explains superconductors. In superconductors, the bosons that condense are made of pairs of electrons. We call them Cooper pairs, and that is the subject of our discussion today. Okay. So here's a picture of a Cooper pair. Cooper pairs involve electrons bound into pairs by forming a pair of electrons. By combining two fermions, they form a boson, and they're bound by some kind of glue. The origin of this glue may sometimes be mysterious. It's the vibrations of atoms in conventional superconductors, but it may be something else, such as magnetism, and this gives rise to an energy gap. The energy gap preserves the condensate, and the coherence of the condensate leads to supercurrents. When you bend the phase of the condensate, you get a resulting supercurrent, and they flow persistently without resistance. They expel magnetic fields, and this leads to magnetic levitation, as you can see here with a cuprate superconductor. A few more things to understand. In conventional superconductors, Tc is low, the gap is small, and they require liquid helium to cool them down. And here is a plot of Tc versus time since the early part of the 20th century when Kamel and Onnes discovered superconductivity in mercury. And you can see that the first half of the century was involved with discovering conventional superconductors. The highest known Tc of a conventional superconductor at ambient pressure, you'll see there is magnesium diboride. High Tc cuprate superconductors, discovered in 1986 by Ben Norson-Muller, have a much larger gap. And because they've got a larger gap, they have a larger Tc, and they only require liquid nitrogen for their cooling into the superconducting state. This is much cheaper. They also contain a D-wave energy gap, which contains nodes. These nodes protect the Cooper pair against the repulsion of the Coulomb interaction. So here you see the two lines of discovery of the copper-based and the iron-based superconductors. These have various advantages for technology. For example, the iron-based superconductors, though lower Tc, are easier to work with. You can make contacts more easily. So this raises questions pertinent to technology and discovery. Number one, how do we find new superconductors? How do we navigate the periodic table to find that magical combination of elements that will give us even higher Tc superconductivity? Secondly, superconductivity isn't the only form of coherent quantum matter. What new kinds of electron coherence and what new kinds of quantum materials are possible? Thirdly, and you're going to hear about that this afternoon, what are the present and future applications of superconductors? Let's look at that in a bit more detail. Okay. Here are some pictures of various applications. Let me run you through some of them. You're going to hear about transmission lines later this afternoon, zero resistance transmission lines which have liquid nitrogen cooling them to maintain the cuprate superconductor interior below the superconducting transition temperature. Already in action in many accelerators today, there are conventional superconductors driving the magnets that accelerate the particles around the track. MRI has revolutionized medicine, and the improvements in superconductors occurring today will lead to greatly enhanced resolution in the MRI machines of the future, which will run at higher and higher magnetic fields. Maglev trains are under construction, planned for the Tokyo-Kyoto route. These currently work on conventional niobium superconductors, but there are plans to switch them over in the future to high TC magnets. Okay. Something that's driving the superconducting technology today, nuclear fusion, the availability of high TC tapes that can generate high fields has meant that it's possible to design much more compact tokamaks, many times smaller than those of, for example, ITER in Europe. And this is possible because the high energy density of the plasma depends on very high fields, and the energy density goes something like the field to the power of 4. And so if you can increase your field by the factor of 2 or 3, you can make your tokamak much, much smaller. And in particular, Commonwealth Fusion expects to have a working reactor done by the end of this decade. Okay. Here's another example. The particle physicists around the world are thinking about their next colliders. And one possibility is a muon collider, where they'll collide muon anti-muons together to look at physics beyond the standard model. This will require magnets of 24 Tesla built on an industrial scale. This will only be possible with the new technology of new high TC magnets. Okay. So, but what if we want to go beyond the current materials? How do we search for new quantum materials? How do we accelerate our discovery of new quantum materials? And the explorers who set out across the ocean in the time of Isaac Newton were exploring the surface of the Earth, and they relied on new maps. So what new kinds of maps can we make to navigate the ocean of the periodic table? The periodic table is interesting. Of course, it's based on our understanding of the quantum hydrogen atom. But every single element, when we mix them together to make compounds, doesn't just give you a mixture. When you mix different colored sands together, you get sand which has a mixture of the two colors. It's still the same sand. But when you combine hydrogen and oxygen together, you get a completely new material. You get water. And this is because quantum mechanics, through its interference, means that A plus B is not equal to C. And what we have here is a multi-dimensional C that we're navigating. Already, the elements provide us more than 100 possible combinations, and even there, we have different structures. Look at the great advances that have been made just by looking at carbon and learning of new ways to make two-dimensional graphene. But we can go up in dimension to the binary. Already there are probably more than 10,000 binaries barely explored today. Tertiaries more than 1 million, quaternaries more than 100 million. And YBCO, this high temperature superconductor, is just one of them. How can you say there are no superconductors with TC higher than 100 or 120 Kelvin amongst this vast space of possibilities? And how can you explore it? And what are the strategies? Some will say, well, what about AI? Let's use AI to explore this universe. Well, let me tell you something. AI only works if you have good data to learn on. And so we need new data. Let me keep going. We require new material databases, including those that tell us about failed syntheses. We still don't understand how correlated matter really works. We need new intellectual concepts. For example, strange metals and quantum critical points are examples of phenomena that we only just understand. And lastly, if we're really to make the kind of discoveries that were made, for example, at Bell Labs in the last century, We need new industry academic partnerships. Thank you.
Thank you very much for your insight for first speech. So we'll continue later the questions. Thank you. And having heard of great theoretical or general perspective on the superconductivity and quantum materials, let me proceed to the second speaker, talking about various aspects of real materials, including high TC cuprate, ion-based superconductors, etc., etc. So let me introduce the renowned scholar from China, Professor Haihu Wen. So he will be talking on this material aspect. He's very known also scholar. Actually, he was also again 2013 APS fellow. He got Yangtze River Scholarship Professor and many Asian awards as well. So let's welcome Professor Haihu Wen.
Okay, good afternoon, everyone. I'm very happy to be here. First of all, I thank the organizer, especially Professor Ki-Hung Kim, for inviting me to be here. The title of my talk is Current Status and Issues on High-Temperature Superconductivity. I will mainly talk about the cuprates and the ion-based superconductors. This is a very big title. I was assigned with this title, so I'm happy to touch some physics about that. My name is Haihu Wen from Nanjing University, China. As just you heard from Professor Piers Coleman, that superconductivity was discovered by company owners in 1911 in a group. The group was in Leiden, okay, Holland. So they found the mercury, the resistivity of mercury dropped to finite, almost to zero at a finite temperature. Okay, so nowadays we can have the superconductors with transition temperature far above 100 Kelvin. This one's mercury 1223, so you can see that it's 35 Kelvin transition temperature. Okay. So concerning this mechanism for superconductivity, it was until this paper published in 1957 by Buding, Cooper, Schaffer. So they proposed in the paper that the BCS, according to the BCS theory, the normal state is a Landau Fermi liquid. Okay. Then the second is that the two electrons will pair up to form the Cooper pairs through exchanging this lattice phonon, this lattice vibration we call phonon. Then the Cooper pairs will behave as a charge carriers, condense into a low energy state, which is protected by an energy gap. Yeah. Pierce just mentioned that. So the gap function, according to the gap function here, it is closely related to the pairing interaction of the two electrons, V here. Okay, so the V is a pairing interaction function, and will form a gap function in the superconducting state. So gap is a momentum-dependent function. You can see that if the V is negative for the phonon-mediated pairing, then we would expect a same sign gap on the Fermi surface. Yeah, so the gap will not change sign. However, if the V is a positive, for example, by exchanging the magnetic super exchange, okay, the magnetic spin fluctuations, then we are left with the consequence that the gap should change sign on the Fermi surface. That's a very important point for the unconventional superconductors. So in 1986, Benoist and Miller found high-temperature superconductivity in the cuprate. The early materials is a barium-doped lanthanum 214 compound. Nowadays, we know that there are about 100 compounds coming from the cuprate. And the major player here is this carboxygen plane, okay? But this parent phase, actually, if you have a look at the energy levels or the DFT, the band theory calculation, you will see that it should be metal. But somehow it is not a metal, it is insulator, okay? But this insulating is not due to the band insulating. It's just due to the strong correlation. So as early in 1987, Philip Anderson pointed out already that the superconductivity is induced by doping to the multi-insulator. And also the ordinary Landau Fermi liquid picture fails to describe the normal state of the cuprate, okay? So with that, I think the superconductivity is certainly very different from what we expect from the phonon-mediated picture. So the parent phase is a multi-insulator. By doping holes, we have this strand metal region, and when lower temperature, we can get a superconducting state, okay? So the superconductivity is due to the strong correlation effect. It's not due to the phonon-mediated pairing. That's simple. So we have a lot of new questions can be raised in this field. And the key issues is how do two electrons pair up, and how is the phase coherence established, and how to describe the normal state with abnormal properties, okay? In 2005, the Science magazine selected 125 most challenging scientific questions of human beings so far. So one of the questions listed as 42 says that what is a microscopic mechanism for high temperature superconductivity? So you can imagine how important it is. It is one of the 25 questions we are facing now at this moment. Yeah. Okay. So let me come back to the gap function again. So as I said, that if the pairing interaction V is positive, we are left with a sign change result. Okay, so for the cuprate, we would expect a so-called D wave. So the gap would change sign from positive, negative, positive. But for ion-based superconductors, because we have several sets of Fermi pockets, so in that case, the situation would be that the gap will change sign across the Fermi pocket, different Fermi pocket. So that will lead to so-called S plus minus pairing. But experimentally, to prove that is not so easy. So for the cuprate, the D-wave pairing symmetry has been proved by many experiments. One of the typical one is from Changqi Cui and Kirtley et al. They made this beautiful tri-crystal, and according to the D-wave pairing symmetry, there should be a Josephson current simultaneously produce a half-flux quanta at the center, and they found this half-flux quanta here. So that gives a strong support to the D-wave pairing. And recently in our group, we use a new technique we call STM, based on STM measurement. We measured the quasi-particle interference message. And we use a new method called phase referenced QPI. And according to the D-wave pairing symmetry, the 7 scattering vectors would produce 4 scattering for the opposite sign and 3 with the same sign. Then from the data, you can find that result, okay? So this gives a new method to support the D-wave pairing symmetry very, very well, yeah. And concerning the pairing, we did the tunneling measurement in the underdoped cuprate. What we found is that very interesting. So the two holes somehow seems to be bound into a bound state, paired state. And the low energy the density state shows something look like in the superconducting state. You can see this peak. Looks like the Bogoliubov dispersion in the superconducting state. Okay, so we would propose that the two-hole bound state might be the precursor format of the Cooper pairing. So the two holes would be form a bound state and confined in the real space in the 4A by 4A region. Okay. So in the cuprate, we now know that the single particle tunneling measures the local pairing energy, and the Andreev reflection measures the phase coherence energy. You can see that these two energies evolve in a two different ways. This one is the pairing energy, and this one is the phase coherence energy. So it seems that in the cuprate, clearly, the pairing and the phase coherence are happening in the two steps. It's not like a BCS case in the same simultaneously. In 2006, Professor Hosono's group found high temperature superconductivity in the ion-based superconductors with a TC about 26 Kelvin. And quickly, many new structures have been found with different superconducting transition temperatures. One of the common shared layer is this ion arsenic and ion selenium layers. The superconductivity occurs in this layer. And it's, as I said, that if the repulsive interaction for the pairing, we would expect S plus minus pairing symmetry, okay? But it's very difficult to prove that because the adjustment effect cannot be used to test that. So then we use the quantum impurity. Here we use a non-magnetic quantum impurity like a couple in the sample. So we go to a single crystal with such impurities. So according to the theory, if you see this in-gap state by the non-magnetic impurity, that would suggest the sign change of the gap. Okay, so this set of data gives us strong and solid evidence for the S plus minus pairing. Yeah, and for ion-based superconductors, we have another set of materials, which is ion selenium without the hole pocket. But even with that material, without the hole pocket, we found that we use this so-called phase reference QPI. We got this quantity, and we found that the experiment measured the data looks like this, and the S plus minus, the model calculation gives by this blue solid line here. You can see that our experiment data and the theoretical curve looks very consistent very well. Yeah. So for the ion-based superconductor, we also found another interesting thing is that the Fermi energy is very small. We know that in the BCS theory, the Fermi energy is much, much larger than the pairing gap. But in the ion-based superconductors, we follow this theory given by Deschamps and the co-workers that they proposed in 1964. In the vortex core center, there is a bound state, okay, we call vortex core bound state. According to the theory, if the Fermi energy is small enough, then these energy levels can be measured by the tunneling. So the theoretically proposed value ratio is 1/3/5. And our data shows that it's 1/2.7/4.2. You can see the three energy levels here. So that indeed shows that the Fermi energy is very small. But if we use a simple calculation formula, then this Fermi energy divided to the gap would mean that would give this so-called Cooper pair number within per coherence volume. So that if the Fermi energy is comparable to energy gap, would mean that in the per coherence volume, the Cooper pair number is very limited. So that makes the case more close to the BEC case, okay? So now I use this. In the BCS, as I said, the theoretical result is that the superconducting transition is determined by the gap. But in the local pairing, with a strong local pairing and the diluted superfluid density, then the transition temperature is determined by the superfluid density. It's not by the gap. So with that, let me come to the last page of my talk. So from the weak coupling, phonomediated to magnetic superexchange to the local pairing. So we propose a generic paradigm for superconductivity. You can see that the superconducting region sitting in this small corner. And in this limit, we have local pairing and with finite superfluid density, and which may correspond to the underdoped cuprate. And in between, it looks the ion-based superconductors probably located in between, corresponding to the BCS to BC crossover region. So our conclusion is that we need to pay more attention to the local pair and the BC-like condensation. And the room temperature could be made with a strong local pairing and suitable superfluid density. Okay, so with that, I thank you very much for your attention.
Thank you very much for covering up the cuprate and ion-based superconductors. So thank you. So let me welcome our third speaker. So as a group leader, as a young leader, he's Professor Dr. Seung-Hyun Kim. I will introduce him. He's currently group leader at the Max Planck Institute for Chemical Physics of Solids at Dresden. So he will today talk on the cerium-based superconductors, also heavy permanent superconductors, another area of exciting superconducting material set. So let's welcome Dr. Kim.
Okay, thanks to the organizer and especially this Professor Ki-Yoon Kim for actually having me here today. So yeah, today I'm gonna talk about some emerging superconducting materials and emergent odor. So yes, so actually Pierce and the Haihu actually introduced a quite broad introduction with their actually experience and a wide point of view. So which is allow me to talk about something more specific. Okay. So actually, I was asked to talk about this, the emergent superconducting materials and emergent odor. So actually, I have asked actually ChatGPT, what are there's a recently emerging actually superconducting system. So the first answer was the hydrogen sulfide actually system under high pressure. So which is quite one of the hot topic actually toward the room temperature superconductor. So in this system, so we understood that we have established understanding that the superconducting pairing is given by a lattice modulation, actually, which is placed as a pairing glue. Yes, and actually, and based on actually this picture, so the light element and this the high pressure actually promote actually this pairing strengths, actually, which can lead to a room temperature superconductivity. And the further compounds are actually this class of material. So cuprate superconductor and iron-based superconductor. So the Haihu actually already introduced. And one of the this active topic is on this topological superconductor as well. And quite recently, so we actually have found a very interesting phenomena in this twisted bilayer graphene. So and I would add some more actually compound actually including a Kagome superconductor and also the iron-based, the recently actually discovered the uranium-based, the heavy fermion superconductor, and also this nickelate superconductor as well. So I would say those compounds actually can be called as this unconventional superconductor. So different from this, the previous actually the superconductor. So actually we haven't actually established a quite clear understanding what is the pairing mechanism on those superconductors. So one of the strong candidates is the strong the spin fluctuation, and because this spin fluctuation gives us can promise a high, very strong actually the pairing potential, which actually can give us also have a chance toward this room temperature superconductor. Okay, so then what are some common features among this the unconventional superconductor? So I would say there are several the common features, and first thing is that they are mostly most of the compound has the layered structure, right? So in this layered structure, actually electrons are confined in a layers or sometimes in a chain. So electrons actually bump to each other quite frequently. So electrons are actually quite uncompatible actually. So in this structure, so then actually because electrons are confined to a low dimensional, so they actually correlate, they interact quite strongly in each other. And also they have a spin or orbital or charge degree freedom. So on those channels, actually the electrons interact quite strongly. So, and because of those interactions, so because the electrons feel comfortable, they try to actually minimize their energy. They try to find some more actually stable state. So by that mechanism, actually, we can find several actually odors at low temperature. So, and actually the superconductivity is one of the state. Actually, electron can organize themselves to lower energy. So once we found some actually that material which has some ordering state from this electron correlation, then by tuning the system, then we could also realize the superconductivity. And also one of these the key actually top understanding covering those things are the quantum criticality. So once the ordering temperature is suppressed by some tuning parameter, then because of this quantum uncertainty principle, so electron fluctuation is quite enhanced, and such kind of actually the quantum feature actually can be extended to a higher temperature. So in order to actually avoid such kind of this high fluctuation, the electrons actually decide to go into a superconducting state. So actually, so I actually work on the material synthesis lab. So I think those features are a kind of guide or map actually to find a new quantum system which has this kind of interesting the quantum features. Okay, so I think I can introduce one of a superconductor. I have discovered myself in 2021. So I think it is a good example actually how to find a new superconductor. So this is the compound of cerium, rhodium to arsenic 2. It's so-called the heavy fermion superconductor. Even though TC is quite low, it's 0.3 Kelvin, but actually it actually shows a really interesting phenomena under magnetic field. So yes, and actually I can remind you actually what is the feature of this superconductor which shares with actually previous studied compounds. So first of all, actually this compound is also a layer structure. As you can see, there are actually well-defined rhodium arsenic layers, which is sandwiched by the cerium. Okay, and it has a strong correlation. So I think it is the heat capacity as a function of temperature data actually will represent the property of this compound. As you can see, this heat capacity C/T value is 2 joule per mole Kelvin square. It is substantially larger than the usual metal, which has just 1 millijoule per mole Kelvin square. So this large actually heat capacity value represent this strong electronic correlation. And it has actually neighboring competing order, so it has additional the anomalous feature above TC. So I think it's already actually this system try to find a stable actually state, and actually this state they further actually develop into superconducting state. And it also shows the quantum criticality. So usually conventional metal, the C/T capacity is a constant at low temperature. However, it shows some diverging behavior. So this represents that this system is quite close to the quantum critical point. Okay, so what is interesting feature in this low TC, unfortunately, superconductor? Okay, this is a magnetic phase diagram of this superconductor. So interestingly, we have some kink feature on the magnetic field, and we found a very robust actually evidence of a phase transition within the superconducting state. Okay, so and our understanding is like that. So at low magnetic field, you can see that superconductivity is quite quickly suppressed by magnetic field, and which then I think it is behavior like a spin singlet superconductor. But we can actually pay attention to the crystal structure of this compound. So in this compound, there are actually 2 cerium sites in the unit cell, which has a different local environment. So here you can see this gray is arsenic and cerium is blue, and rhodium is green. So order is arsenic, cerium, rhodium. However, if you move to the other layer in the unit cell, this order is reversed, which makes this local image symmetry breaking on the cerium side. Okay, so these allow us to actually a additional degree of freedom for superconducting order parameter. So one possible combination is that just the superconducting order parameter is constant along those layers. Okay, then this system can actually have this S wave or D wave spin singlet superconducting state. However, interestingly, actually, this degree of freedom allows this kind of superconducting order parameter because superconducting order parameter is the quantum actually quantity, so it can have this phase as well. So that actually allows the superconducting order parameter actually to modulate along these layers. So if we have this kind of plus minus modulation on each layer, it gives us this P wave like superconducting state, which is quite consistent with this boost of superconductivity on the magnetic field. Okay, So this is a quite unique system actually to allow the both of these superconductivity, all the parameter in a single system, which is tuned by magnetic field. Okay. And this high field state can be actually candidate for a topological superconductivity as well. Okay, so let me summarize. So I think it's an unconventional superconductor state is just one of the possible state of matter, which is interacting electrons can organize themselves. So once we have this strong the correlation, like is some pattern in this bird clock, there's some pattern. There could be some kind of state of matter as well. So I think it's important to actually broadly study the quantum materials, and then it promises the unconventional superconductivity, and in my case as well, sometimes we could find a very exotic superconductor as well. Okay, thanks for your attention.
Thank you very much, Dr. Kim. He has actually provided very good insight to how to find the unconventional superconductor and to boost up the unconventional electron pairing. So let me move to next speaker. So from China again, Professor Jian Wang. He's actually Boya Distinguished Professor at International Center for Quantum Materials and School of Beijing University. So he is going to talk today another class of material, particularly two-dimensional and interface superconductivity in crystalline system. Let's hear a new aspect of superconductivity from him.
Okay. Thank the organizers for the invitation. It's my great pleasure to attend this wonderful workshop. My name is Jian Wang, and I'm from Peking University. Today, my topic is two-dimensional superconductivity in crystalline systems. Okay, Nobel Prizes were awarded to superconductivity 5 times, since superconductivity is an important topic in science. There are 2 basic phenomena for superconductivity. The first is the disappearance of resistance, and the second is a perfect diamagnetism. It's also called Meissner effect. So what's a two-dimensional superconductivity, or 2D superconductivity? We know, according to the BCS theory, 2 electrons can form Cooper pairs. The superfluid of Cooper pairs forms a superconducting state. So the size of a Cooper pair, we call it superconducting coherence length, psi. Yeah, or the distance of the 2 electrons. So if you have a superconductor, the superconductor size is large enough and much larger than the superconducting coherence length psi. So the Cooper pairs can move in this sample freely in all directions. Then we can call it a 3D superconductor. But if the thickness of a superconductor is thin enough, less than the coherence length, then the Cooper pairs can only move in a plane. We can call it a 2D superconductor. Okay, why superconductor important? Let's look over human history. We were in Stone Age, yeah, but we can also call it Insulator Age. After that, we went into the Iron Age. Of course, we can also call it Conductor Age. Today, we are in the Information Age, but we can also call it Semiconductor Age. How about tomorrow? Is it possible superconductor age? We all have the dream and aim one day. The room temperature superconductor can be realized and change the world. Okay, actually superconductors have been applied in electronics and electricity. Okay, why 2D crystalline superconductors? First, an ideal platform to study quantum phase transitions and ground state due to the strong fluctuations in 2D systems. Second, a simple platform to study and understand the unconventional high-TC superconducting states. We know all high-TC superconductors, they are layered structure, yeah? And topological superconducting states and other emergent quantum states. Third, an important system to develop superconducting electronics. Note that our present information technology is based on the in-plane fabrication technique. Okay, part one, quantum phase transitions in 2D crystalline superconductors. We know the superconducting insulator transition is a paradigm of quantum phase transition. That's why it was awarded the Berkeley Prize. Why quantum phase transition is important? Quantum phase transition is a phase transition happens at 0 temperature. Comparing to a classical phase transition, our understanding and knowledge on the quantum phase transition is limited. So it's important. A 2D superconductor can offer a very good platform to study quantum phase transitions. For example, new quantum phase transition can be found in 2D crystalline superconductors. Here's an example, quantum Griffith singularity. You can see this figure, the resistance versus magnetic field at different temperatures. You can see all the curves across a region. And according to this data, you can find the dynamical critical exponent is divergent when the system approaching a quantum criticality. That's because the quenched disorder dominates at very low temperatures. So it can be called randomness rules. Yeah, randomness or disorder at ultra low temperatures makes such quantum phase transition happen. Okay, normally people believe there are 2 ground states for a 2D superconducting system. Yeah, please see this figure, and one state is a superfluid or superconductor state. The other state is an insulating state. Between these 2 states, there's this point is quantum criticality. However, more and more works suggest that there's a 3rd ground state in 2D superconductors. People call it anomalous metallic state or quantum metal state. Here's an example. Here's the high TC YBCO films. It's a nano patterned film. When you measure such a film, you can see such resistance saturation at ultra low temperatures. Yeah, you can see that. It's not 0 resistance. It's not insulating state. It's a metallic state. And since the film is nano patterned, so we can measure quantum oscillations. The quantum oscillations show that even in such quantum metal state, Cooper pairs dominate the transport behavior. So it's called both metal uncaged, or bosons can exist as a metal. Also, Professor Wilson call it, if it's true, this conclusion is of fundamental importance for our understanding for quantum materials. Okay, part 2, high TC superconductivity and emergent quantum states in 2D crystalline superconductors. Here's an example. You can see here's a 1 unit cell thick iron selenide film grew on STO substrate by MBE technique. Yeah, the thickness of the film is only 0.55 nanometer. So it's very thin. So by transport measurements, we can see the onset TC is above 40 Kelvin, so it's a high TC superconductor. It's a high TC superconductor at a 2D limit. You can even detect the Meissner effect of such a thin high TC superconductor. And the second example is a high TC superconductivity observed in topological superconductor candidate 1 unit cell thick iron tellurium selenide film grow on STO substrate. You can see this is an atomic structure of such a film, and this superconducting gap behavior of this film. And the estimated TC is around 62 Kelvin. So it's a high TC 2D superconductor. Okay, in such a high TC 2D superconductor, we can observe the evidences of Majorana non-bound states. You can say that at some certain iron at atoms, you can see the zero energy bound states. And at both ends of a one-dimensional atomic light defect, you can see such a zero energy bound states. And the behaviors are consistent with the expectation of a Majorana bound states. And future directions how to manipulate such Majorana bound states, because it's the one way to realize topological quantum bits. Okay, the third example is a pair-density wave state in the 2D crystalline high-TC superconductor. What's a PDW state? PDW state is a superconducting state without applying a magnetic field, with a spatially modulated, like this, order parameter, superconducting order parameter. It's due to the finite momentum of Cooper pairing. So today, people believe that PDW state is a principal state in unconventional high-TC superconductors. It's an emergent quantum state. And in 2D high-TC superconductors, along such special domain wall, we can see the local density states modulations, yeah, like this picture. And we can also see the coherence peaks modulations, yeah, like this picture. And we can also observe the superconducting gap value modulations. So all these results are the evidences of a pair density wave state. So indeed, in such a 2D high-TC superconducting system, we can study an emergent quantum state, PDW state. Okay, last part, superconducting electronics based on 2D superconductors. I just gave 2 examples. One example is superconducting quantum bits. We know superconducting Josephson junctions based on superconducting aluminum films are used to fabricate superconducting quantum bits like this. But the TC, the critical temperature of aluminum film, is very, very low. So we have to use ultra low temperature dilution system to operate such quantum bits. How about other superconducting films to replace the aluminum film? For example, high TC superconducting film. If successful, at least we don't need the ultra low temperature dilution system anymore. Okay, the other example is superconducting diode effect. In 2020, people found the superconductor can also show superconducting diode effect with magnetic field. Soon after that, in 2022, field-free, that means magnetic field-free superconducting diode effect were observed. In future, next step, if we can realize superconducting diode with a higher working temperature and a simple configuration, then maybe can be used in electronics. Okay, perspective of superconductivity at 2D crystalline materials. Is it next generation quantum materials of information age? At least it's for the science, it's an endless frontier, because 2D superconductivity is a parsing platform for quantum phase transitions, high TC superconductivity, topological superconductivity, emergent quantum phenomena, superconducting electronics, and so on. Thank you. Thank you for your attention.
Thank you, Professor Wang. So he indeed has covered the fundamentals of 2D material as well as the future direction of applications. And one of them includes actually quantum computer project. And I think we can elaborate this subject by our 5th speaker, Professor Yongju Do. He's currently working as a professor at GIST. He's actually leader for mesoscopic physics and Joseph junctions and topological superconductivity. So he's currently leading this CRI leader research grant, and the 2017 Samsung Future Technology grant, he got it. So let's hear from him about a new state of matter, Majorana fermions and topological solids. Let's welcome Professor Do.
Thank you, Guillaume, for the nice introductions. And I'm Yongju Do from Gwangju Institute of Science and Technology. And I thank you, everyone in this room, for coming here and Also, I thank to the unknown audience who will watch this seminar via the internet. The title of my talk is the hunting for majorana fermions in topological solids. So in recent years, I have worked on the hybrid systems of the superconductor and the topological materials, and then to search for the majorana zero mode as a basis building blocks for the topological quantum computations. So the first start is the Kamaring Onnes again. So he has discovered the superconductivity 100 years ago, and then he used the material of the mercury. And after then, half century later, the Baden-Cooper and Schuriper has proposed the idea to explain the conventional superconductivity by using the Cooper pairs. The two electrons make a pair, and then they can transmit the electric charge without generating any voltage dissipation. After then, Joepson, the young physics student at the Cambridge University, has proposed a very interesting idea. When we have two superconductors, and then we put them very closely, 1 nanometer thick away, and then the Cooper pairs in one of the superconductor can tunnel through the barrier without making any voltage dissipation to the next superconducting electrode. So we can measure the supercurrent without any generation of the resistance. And this is the supercurrent. He has made very simple two equations to describe this supercurrent. And the supercurrent is proportional to the sinusoidal function of the pi, and pi is the phase difference between two spawning electrodes. And when you apply the voltage bias on this device, the V, then actually the pi shows the time-dependent behaviors. So those two equations governs the whole Joepson junctions, and then actually they are used to develop a quantum computation at this moment. And his original idea, he thought about the insulating barrier, but when we replace the insulator to the normal metal, actually his idea still works. So we can see in the voltage and current curves, we can see the zero voltage current. So that is the supercurrent. It has the maximum value of the critical current. And when we shine the microwave on these devices, then we can see some particular quantized voltage steps occurs in this IV curve. And those voltage steps is determined by the microwave frequency and Planck constant and the electrical charge exactly satisfying the Joepson-AC relation. We call these voltage steps as the Shapiro steps. But Ettore Majorana, the Italian physicist, has proposed the idea of the Majorana fermions. And actually he found out the real wave function solution of the Dirac equations, which is the relativistic Schrödinger equations. And his real wave solution means that the Majorana fermion is a particle that is equal to its own antiparticle. And after his theoretical suggestion, people still working on to find out the evidence of the Majorana fermion, but it is not clear yet. But some years ago, the theoretical condensed matter theorist has proposed the idea of the Majorana zero mode. Very similar, is a condensed matter replica version of the Majorana fermions. And when we have a spawning electrode, and which is coupled to the semiconductor nanowire with a very strong spin-orbit coupling, or the topological insulated nanowires, then we can generate the topological superconductors at the edge or boundary of that junctions. Then we can generate the two Majorana bound states, and that is called as Majorana zero mode. And the interesting thing for this exotic quantum state, they can be used as, to develop a topological quantum computations in solid state versions. The proposing actually the promising the material platforms to host that Majorana zero mode is the 35 nanowire systems or topological insulators. But at this moment, actually we don't have the concrete evidence to prove the existence of Majorana zero mode. It is still elusive. Theoretically, it was suggested that if we observe the conductance peak the amount of the 2 of H at the zero bias voltage, then it can be an evidence of the minor zero mode. But the other origins, such as the quantum physics, can generate similar results. So, and then the other way is that if we have the Job junctions to host the minor zero mode, then the Josephson-H relation is deformed to host the Shapiro step doubling. So now the quantized voltage satisfy the relation HF over E instead of 2E. And also the supercurrent via the minor zero mode follows through in the form of the sine function of the pi over 2 instead of the phi in the conventional Job junctions. So these conductance peak or Shapiro step doubling has already been reported some other groups, but even for this Shapiro step doubling has the another route to generate the signals via the non-topological origins such as Landau Gino transition, etc. So honestly, we don't have that evidence yet. But when you are searching for the minor zero mode, then we thought about the Job junctions. It's a very basic cartoon. This cartoon is from the very basic textbook for the Job junctions. Actually, the real Job junctions has the supercurrent terms, and also it has the capacitive terms and the resistive terms. So the current is the sum of the supercurrent and ohmic normal current and then displacement current. If we combine this equation with the DC and AC Josephson relations, then we can get this equation of motion for to describe the phase difference pi. But this equation is exactly the same form of the equation of motion of the mass particle in the classical mechanics, moving inside this kind of the sinusoidal potentials. And this potentials is given by the cosine pi functions and also the linear function of the pi. And then this is the the bias current I applied for these junctions. So when the bias is 0, then in the particle reside on this minimum point of these potentials. But when I increase the bias current, then we have the slope in the washboard potential walls. And then finally, the particle can escape from the potential wear, and then it can roll off to the downside. If it moves, then it means that the time-dependent change of the phase difference pi, if it is so, then you have the voltage dissipations. So this kind of the escaping motion of the phase particle out of this potential wear corresponds to this switching event in these Job junctions we observe in the IV curve. And usually, this is the stochastic behavior. Usually, we repeat this measurement of the switching event several thousand times. And then every switching event, we record the critical current. And then we can get this kind of the distribution. This is the switching current distributions. But this kind of the work was started from the 1970s around. But now, in our system, whatever topological junctions we have, but if it is not ideally 100% topological junctions, then we have the mixture of the supercurrent, of the conventional supercurrent with the term of the sine pi, and also the topological current with the term of the sine pi over 2. If we have this kind of the mixed current, then our potentials corresponding to this mixed current would have two terms, cosine pi and cosine pi over 2. If I draw it, then actually it shows this kind of the washboard potential with the two different double wells. One is a shallow well, the other one is a deep wells. If I apply the bias current, then the phase particle can escape from the deep well or shallow well. As a result of this, the existence of two different wells, then our switching current distributions would have this kind of the two bimodal features. That is our idea. So if we observe this kind of things, then actually we can give this, you can use this as an evidence for the existence of the minor zero mode in our systems. So we have used this kind of topological insular nanoribbon. The antimony doped bismuth selenide was grown by the Professor Dong Yu at the UC Davis. It has the rectangular shape in the cross-sectional way, and then the width has the overall length scale of the 400 nanometer, and thickness is 100 nanometers. And then we deposited the superconducting films on it for the superconducting electrode, the lead-indium alloy. And then when we measure the IV curve, then we could observe this kind of the hysteretic IV curve. So our critical current is about 10 microamp, and then the return current has the different values from the critical current. Our measurement was done in the dilution fridge, and then we adopted many filters, and the base temperature was 7 millikelvin around. Now, we have measured the switching current distribution in these devices. So this is the 1.8 Kelvin data, and then when we cool down the sample down to the 9 millikelvin, then relatively sharp, very sharp transition, switching events we can observe at the higher temperatures. But when you cool down the devices, then actually it becomes broadened. And then at the very low temperatures, then actually we can observe the very broadening feature of the switching current distributions. But this red dashed part is very different from our previous observations from the conventional junctions made of the graphene or the other semiconductor wires. So very sharp at the higher temperature, but the broadening occurs in the intermediate temperatures. But at the very low temperature, it becomes sharper again. And then that is the very typical features showing the macroscopic quantum tunneling in these quantum wells. But we have the broadening, and then if we have the magnified view, then we can see some kind of the two different, switching peaks here. So if we plot the switching current distribution, the experimental data, we can convert this to the switching rate. And then the switching rate shows that at the relatively high temperature, 1.4 Kelvin or 0.6 Kelvin, it shows the single branches. But the low temperatures below 0.5 Kelvin, then the gamma shows that two different branches doesn't really exist. It means that it indicates that we have two different potential wells. Actually, the more detailed the theoretical analysis was done by the collaboration with the theory group at KAIST, Professor Hung-Sun Sim's group. And then, so I skipped the details, but the red lines is the numerical calculations from that theory, and then the black dots is our data. So out of this, then we can extract two parameters. One is the Popeye critical current, 250 nanoamp at the base temperatures. But this experimental value can be compared with the theoretical value because theoretically the Popeye current depends on only the superconducting gap energy delta. And then the delta we can extract it from the multiple undulating reflections. I skipped the part here, but if we use that delta value measured from the multiple undulating reflection, then the theoretical value is 320 nanoampere. And then actually this is the value for the ideal transparencies. So relatively smaller values of the IC Popeye from this theoretical value can be caused by the finite transparency in our junctions. And now we have shined the junctions with the microwave. And then this is the color plot showing that the integer index of the Shapiro steps. So n equal 1 step is missing here, meaning that the Shapiro step missing is observed in our system, but the temperature was 10 millikelvin. If we increase the temperature up to the 0.8 Kelvin, 1.0 Kelvin, 1.2 Kelvin, still we can see n equal 2 step is observable, but n equal 1 step is missing. So Shapiro step missing is observed up to the 1.2 Kelvin, the highest temperature so far. But the combination of the switching current distribution and Shapiro steps has different meaning. We observed the bimodal switching current distribution as we expected before, but it doesn't mean that the periodicity of the potential well, whether it has the 2 pi or 4 pi or pi period, whatever, but it only says that we have two different periodicity in our potential wells. But we don't know what is the periodicities. But that periodicity can be observed by using these Shapiro steps. The Shapiro step shows the n equal 1 step missing, and then it means that we have 4 pi current terms, and 2 pi is the conventional terms. So our observations is from the 2 pi and 4 pi periodic potential wells. And then if we combine those two switching current distributions and then Shapiro steps, it can be used to verify the existence of topological supercurrent in various kinds of topological junctions. And this is the summary, and then thank you for your attention.
Yeah, thank you very much for showing how we proved the Majorana fermion out of current distribution of junctions. And So thanks for your patience, and then let me introduce our last speaker. So Professor Seung-Young Han is actually leading scientist working on application of high-tech superconductors and particularly future magnet design. He's a currently professor at Department of Electrical Engineering, Electrical Computer Engineering in Seoul University. He got 2019 Top 10 Breakthroughs Physics World Award and also 21 April Scientist of the Month Award from NRF Korea. So he will show real practical world to apply these superconducting high TC wires and how to make a good magnet for future application in the society, also in the R&D area. So let's welcome Professor Han.
Thank you. Probably I am the only engineer among speakers today, so I'm not a scientist. I'd rather represent myself as an engineer. So today I'm going to talk about superconducting magnet and its applications. So I have two parts. The first part is why the community has not seen so many applications so far, if the superconductor is that good. The second part is there was some breakthrough which I contributed so far, and this breakthrough actually impacts the horizon of new superconducting magnet and its application. So that's the second part of my talk. Professor Coleman took my thunder already, so he showed multiple interesting applications already in his talk, and so probably I'll skip this part. So basically, superconducting application, you might be categorized into two parts. The first part is whether my major is using the high field and large current application. We often call the large scale application. The second part, definitely electronics. The famous part is actually quantum computing. So today, my talk is more focusing on the large scale application, although my group is also working on electronics too. So superconductivity, again, speakers already said is 100 years old. Every year, superconductivity is future technology. So then one might think, why the hell these people do them so far? Why we haven't seen such many applications if this is that good? So if somebody asks, in a particularly high temperature superconductor is nearly 40 years old. Yes, I'm getting older, I guess. So after 40 years, what happened and why we haven't seen so many high temperature superconductor in abbreviation HTS applications so far? If one might ask me to pick up the one particular technical challenge, I might rather choose quench protection, which I'll briefly explain. So this picture is actually taken with my former colleague at MIT, and spending like few months, we built this particular high temperature superconductor magnet for some science application. And this is why we took the picture in the morning to memory. And usually, most superconducting magnets suddenly lose its superconductivity. We often call it, our terminology, quench. There are a lot of different reasons to initiate the quench. One of the typical reasons is operator's failure, humans' mistake. So when quench occurs, this is what happened. In just like a few seconds, your superconducting magnet burned like that, electrical burnout. This is actually kind of a nightmare for particularly high temperature superconducting magnet engineers. So this is actually schematic view. If I explain a little engineering way, here the circular lines, gray color represents your high temperature superconducting wire. It is wound spirally. And then black line represents your electrical insulation that works in a way to control. The yellow line represents your magnetic current, electrical current. And then usually quench occurs like a 3 centimeter wide. And then it burns out just like 2 or 3 seconds. So huge amount of effort has been devoted to avoid this kind of quench, or at least deal with the quench with a very modern, top-tier, state-of-the-art power electronic system in a way to deal with this quench problem. So back in 2009, actually, when I was in MIT, I proposed this very simple idea. We name it no insulation. The no insulation, as the name tells, eliminating the electrical insulation intentionally, completely. So what happened is, even though the quench occurred, now the current might bypass the initial quench spot, and then things can be protected. So first I really reported this idea to our community, and for several years, there are a lot of discussion. Now this particular movie released by my colleague, former colleague, Dr. Ki-Duk Shim of Korea Electrical Research Institute. And in this particular movie, as you can see, that they have like a 0.5 meter long coil in the bath of liquid nitrogen. In the fully charged, they are doing this kind of job, nailing, drilling, and literally torturing the coils. So this movie really surprised our community, because so far, high temperature superconductor, which is cuprate material, which is really brittle, therefore, teeny tiny mechanical damage is actually break down the entire magnet. Yet, this no-insulation magnet, for some reason, some engineering reason, is survived. Therefore, we might be able to have a new philosophy to protect high-temperature superconductor magnet. That's the message of this particular movie. So, in fact, this is not a new idea. It is kind of old idea. Now it's pretty popular nowadays, in particularly applied superconductivity. So far, quite a many high-temperature superconductor magnet has been built with this no-insulation technique incorporated. This is kind of brief summary. And among them, this is one of my achievements with my colleague in the National Magnetic Field Laboratory. Using this new superconducting winding technique, no insulation, we will be able to make this teeny tiny, small, high-temperature superconducting coil. We often compare this with the toilet paper leftover. If you spend all the toilet paper, you have like a small cylindrical cylinder, paper cylinder. That's the size. I just compare it with my cell phone. So with this HTS magnet, we operate the current density of 1200 ampere millimeter scale, which is extremely high, even 6 times higher than the conventional current density of high temperature superconducting magnet. So, and then this idea was selected one of the top 10 breakthroughs by Physics World, which is a kind of magazine run by Institute of Physics in England. So, and actually applications are quite many. So with the limited time, I'd like to introduce this compact fusion, which by the way, Dr. Corman briefly introduced in his talk today. So fusion, essentially, if I make it really simple, this is like artificial sun, okay? The sun holds its plasma in a way by like its own gravity, okay? But if we want to make the artificial sun on the Earth, we need a container. So superconducting magnet plays a role to contain the plasma on Earth by its unique magnetic field direction. So we called it the toroidal field. And the problem is the size. This is a picture of the ITER, the International Thermonuclear Experimental Reactor, currently being built near the Aix-en-Provence in France. And then the problem is it's huge. The superconducting magnet coil size is 25 meter diameter, which is really, really large. So before I move on, I would like you to remember this particular magnet which I designed when I was in MIT, and then one of the small local startup company in Korea named Sunam, they built this magnet just 1 month after my paper design. Anyway, this magnet reached 26 Tesla back in 2015. At that time, the highest magnetic field from high temperature superconducting magnet. And then, this is, guys, my former boss, MIT, Professor Dennis White, the director of Plasma Science Fusion Center, MIT, at that time, Dean of Department of Nuclear Engineering. He was giving a talk. This is actually screen capture his YouTube lecture. And 2016 February at MIT Clubhouse in California, he was giving a talk and talking about the magnet, the 26 stellar magnet of the tsunami. He just emphasized the importance of this new no-insulation idea, all the good words, and suddenly he's claiming that buying this magnet's engineering parameter, he might be able to build the compact fusion magnet extremely compact. So how compact? This is actually the figure. Right there, that's the human size. Ooh, I can't have time to point it out. That's the human size. So right there, you see the eta. That's not the ore. After the eta, that's the experimental reactor. If you produce the net power, you have to build the demo magnet. That is our human's dream. So MIT team claimed that they can make, using this no-insulation high-temperature superconductor magnet, they can make it way smaller, way faster, therefore way cheaper. So at that time when MIT claimed this idea, it is a rather radical idea. It was just really, there are huge pushback from the conventional ITER program. But then Bill Gates, 2019, suddenly picked this idea, one of his top 10 breaks. He always picked the top 10 breaks every year. So this compact high temperature fusion magnet idea is actually one of his top 10 breakthroughs back in 2019. And suddenly, a small startup created, that's name is Common Fusion System. Actually, friends of my former colleagues at MIT. And September 2021, they physically delivered 20 Tesla, 3-meter long high temperature superconductor magnet to the community, which started a really chaotic situation, even in US. So congressional hearing occurred in 2 months later, November 2021, and then White House, maybe several months later, released a fact sheet. In this fact sheet, they confirmed 5 facts. The first one is, if I read, a privately funded US fusion company, which is CFS, delivered 20 Tesla HTS magnet. That's the fact. And then out of this chaotic situation, they secured 1.8 billion US dollar investment. That's the single most largest investment ever happened to the high temperature superconductor community. So now the game's not over, because that company placed a purchase order of high temperature superconducting wire, nearly 600 million US dollar from the single company. Therefore, last year, very significant, because another challenge, widespread use of high HTS is the conductor cost. Still, it's too expensive. But suddenly, my own experience at SNU, conductor costs dropped like 1/3 just by 1 year. Mainly because now Shanghai Superconductor in China, Faraday factory in Japan, they immediately increased their production capacity in a way to meet the requirement, quotation called by CFS. And few other fusion startups very recently created around the world, including China and Europe, and even Japan. So that is the situation. So this is my last slide. The message I would like to deliver is, see, right now I show you quite many applications. All of these items are currently under R&D globally, and half of these are in progress even in Korea. So application in superconductivity is not really rare. It's in very active area, and with the benefit of this new technology, probably in the future, we might open the new horizon of this, applied superconductivity areas. Thank you for your attention.
Thank you very much, Professor Han. Finalizing this session with the great hope for applying these materials into our society to make our society better, or to make new energy sources. And within less than almost hour, we heard various aspects of superconductivity, starting from old history, how we discover a new material, and how we are applying these ideas of BCS superconductors. Also how we try to find a new state of matter like matter fermion out of unconventional superconductor or topological superconductors. And we are currently heavily using in R&D to the superconducting quantum device for quantum computer devices. And also, Professor Han has elaborated also currently active development of a society to make use of these high TC wires to future to increase this high magnetic field in a limited volume, and how we can utilize this practically to reduce the size of ether plasma confinement, and those things are very vibrant new development. So I'm glad to share this recent activity with the audience here, also audience in the internet. So all of actually our speakers have given presentation, And from now on, we'll have discussions and question and answer session after reorganizing this, after having a little bit of a 5-minute break. Thank you. Everybody's set, and originally we planned to have about 40 minutes. So this was now we are starting. So we originally planned to have about 40-minute discussion and Q&A session. So depending on our speed, we have about 20 minutes left till 5, but we have probably extended this time to up to 5:30. So let me start with that. So I'm an experimentalist working on material synthesis and measurement under extreme physical condition. And as a moderator, I want to introduce also Piers Coleman as another moderator, who is leading scientist in terms of theory of superconductors. So let's welcome Piers. So within our discussion panels, let's ask ourselves, what will be, first of all, your own question inside to discuss out of our talks. So Piers, do you have anything you have in mind?
First of all, let me say that this has been a remarkable array of different opinions. We've got everything from myself, the theoretical physicist, to the hardcore engineers who are really at the working end of trying to make superconductors a practical reality in life. So my question is really, is engineering enough, or would we gain by having a deeper theoretical understanding of some of these phenomena? We heard today from Haihu how most of our understanding of superconductors is still basically built on BCS theory in various different forms. Is that enough for us? Do we need to go beyond that? We didn't hear very much today about the fact that many of these high-temperature superconductors don't form from conventional metals. They form from metals that have a peculiar linear in temperature resistivity. We call it the strange metal. Perhaps we'll have more insight, do you think, into where we can look for higher TC superconductors if we understand the nature of the strange metal that gives rise to these novel superconductors. So I guess the question I'm going to throw out to my experimental friends is, do you really need the theorists, or could we be helpful somehow?
Okay, Piers posed a very nice question to me. Actually, a very, very difficult question. Huh? So I personally believe, certainly now even in the high-temperature superconducting, high-temperature superconductors like iron-based superconductor and the cuprate, we still have some component. Actually, you can reflect from the BCS theory, like the Cooper pair. That's a basic charge carrier, huh? And also you can see that from the tunneling, you can still see the coherence peak. That would mean that the Bogoliubov dispersion somehow keeps the feature now in the superconducting state. But then the question comes in that the correlation effect plays a very big, very important role here. So in that case, so then comes here to many diverse picture. So whether the electron is still that electron in the conventional DFT calculation or the conventional metal, the normal metal. So that's a very good question. And of course, some exotic pictures have been proposed, like electrons have spin-on or Hall-on characters. So that's a good question, and then makes a problem more difficult to consider, to think. But at least there's a strong correlation. As I listed in these 125 questions, actually the 38th question is how to understand the strong correlated system. So it is listed as one of the most challenging questions. So I think the cuprate, especially cuprate, to solve the problem of the cuprate, pairing in the cuprate, I think we are confronted with two important questions. One is how to solve the strong correlated electron systems. And then the second is the pairing mechanism of the cuprate. So as the peers and other friends show that, so the ground state is not that simple. Seems normally now we see clearly the normal state is not a Fermi liquid, okay? Because the superlinear resistivity, that's really a strange metal. And in Pierre's talk, it shows that some kind of some people call it Plancking dissipation. That's already something very interesting and very it is worth to have more demonstration. I mean, how to demonstrate that the electron is really. The basic picture for electrons has been changed a lot or not. So that's very important. I personally believe that concerning the high temperature superconductor, I personally believe that one day the room temperature superconductors can be realized. So far, the room temperature superconductivity, close to room temperature. The highest temperature is 260 Kelvin in the lanthanum hydrogen 10 under pressure about 170 gigapascal. So that one, of course, is based on phonon picture. But then, of course, if we can design some kind of material, at the same time, on one hand, you can keep the structure stable. On the other hand, you have some band of the electrons have the very strong electron-phonon coupling, can sustain this very strong pairing, but at the same time, you keep the structure stable. Okay, that's, I don't know, theoretically, it might be possible if the multiband case, like MGB2. I always use MGB2 as the very good example. So the magnesium atoms form this basic structure, and the boron atoms vibrating very seriously, okay, strongly. That couples to its own p orbitals of the electrons. That makes a very strong electron-phonon coupling. So this could be one route to the high-temperature superconductors at the ambient pressure. Another one could be the strong correlation effect. So in the strong correlation effect, as I showed today, that certainly the magnetism is there. So magnetic superexchange could help the two electrons to pair with a strong local pairing. At least in the field, many people, many theorists or many scientists believe this partial third of this picture. So the magnetic local pairing makes a pairing, very strong pairing there. And at the same time, if we have some finite suitable superfluid density, then we probably can realize the room temperature superconductivity or high temperature superconductivity. Because now in the cuprate, the highest TC is at ambient pressure is 135 Kelvin. But if you have a look at the resistivity, actually it deviates from the high temperature behavior at a much higher temperature, even 200 Kelvin. Yeah, you can see from the curve, it's bending down gradually. So the turning point actually starts at 200 Kelvin or even higher. So that really give us a feeling that the Cooper pairing occurs at a very high temperature. So how to make it phase coherent? So that's the very important point. Okay, so I just add this.
Yeah, summarizing so Haihu's point, I think there are two folds probably way to achieve room temperature superconductivity. One is within the BCS mechanism, you go light element like hydrogen superconductors. And secondly, we make use of a correlation effect to use of strong exchange interactions and local physics to hopefully increase this Cooper pair coherence temperature. So that's kind of twofold. And let me ask intriguing question, Seung-Hyun or Jian, Do you think which mechanism will be more promising? Because Seung-Yeon sort of stressed the correlation effect, but Jian is sort of 2D superconductor way to improve that. So you can answer whatever you think.
Based on the Hai-Hu and Professor Kim's questions, from a 2D superconducting, the point of a 2D superconductors or interface superconductors, we can imagine. Although some materials you need a very high pressure to make it the superconductivity happen or makes the TC critical temperature is very high, but sometimes we can use the interface, use the substrate, and can control the 2D films grow on the substrate. Such a tension or strain may offer same effect with the high pressure. So then we can get the high TC superconductor. We don't need a high pressure and get the high TC superconductor at atmosphere pressure, like that. And this is one way. And also we can use interface or low-dimensional system to design some low-dimensional superconductors. And Professor Wen mentioned, sometimes you need the correlation, strong correlation. Then sometimes in such systems, you have a pressure, you have a correlation. Then maybe even higher TC superconductor can be realized. But we have to try. I'm not sure how much help can be from the theorists. But at least there's a way to do that. Yeah. Okay. Thank you.
Another way of asking to purists is that do you think we can have high TC superconductor, like a theory can be, really proved and developed like BCS?
If you ask different theorists, you get different answers to this. There are some theorists who believe that high-temperature superconductors are basically more or less fully understood within the framework of BCS theory, and they would say the same about ion-based superconductors. But my opinion is that we're only halfway there. If you want to today use artificial intelligence to design materials, you can do very well with weakly correlated materials. I heard how Microsoft was able to use AI to search material space and design a new lithium hydride solid-state battery on a very short period of time. But we can't do the same with strongly correlated materials because we don't understand the basic fabric that gives rise to the high-temperature superconductivity. We don't, as Hai-Hu mentioned, we don't really understand how the pairs are dephasing at high temperatures. We can see signs of the pairs forming, but we don't know how to sustain the phase rigidity over large areas of the crystal. And so we need theory to understand the nature of the strange metal state that has these preformed pairs. We understood BCS theory was possible because we understood the Fermi liquid really very well. And that enabled Bardeen, Cooper, and Schrieffer to simplify the model immensely and produce a very simple model that was very effective. But we don't understand the strange metal at a similar kind of way. In fact, it's my opinion that there are some important aspects missing. One of the key properties of conventional metals is that the electrons are characterized by one scattering rate, one relaxation time. It's a fundamental feature of what's called the Drude model of the electron fluid. But high-temperature superconductors in their normal state show very strongly temperature-dependent Hall constants, which is a signature that there's more than one relaxation rate. The relaxation rate that governs the Hall angle is not the same as the relaxation rate that governs the linear dispersion. We don't understand why. And until we understand why these strange metals work the way they do, we're going to have a very hard time building a simple model of high-temperature superconductivity. And the reason we need those simple models is that we would love to be able to give that theory to a machine and tell it to search for a new structure within compounds containing, say, 6 elements. Okay, we'd love to be able to do that. But we don't know how to do that. So at the moment, we've just got serendipity. We've got the marvelous new ideas of material strategy that my experimental friends have here. And the way we discover new materials is typically we have some idea, we work in some direction, and then something breaks, and hey presto, oh my goodness, I've got a new superconductor. It wasn't intentional. Almost everything is serendipitous at the moment. And so we'd like to find a new way of avoiding that serendipity, of speeding up the process. And this can be by having better theory, but maybe also by following the example of astronomers, using better databases to share our approaches. If we were to share, you may hear that from Song-Hyun, he was saying that 90% or 95% of his material syntheses fail. He has a 5% success rate, okay? And those 95% failures are never published. They go into his notebook, and they're in his lab, and this is being reproduced hundreds of times across the globe. If we had a database where we could store some of this information, we could save time, we could share our collective wisdom, and perhaps we'd actually move ahead much more rapidly. Instead of having 5 different people repeat the same failure in different labs on different continents across the globe, we could maybe have them say, okay, well, that's already been done over here in Korea, so I don't need to go down that avenue, and I can try an alternative avenue. So I think sharing information is the other way we can go ahead. And following the example of the astronomers, have these marvelous databases. We need material databases that enable us to share the experimentalist notebooks. And so we can go through this maze and know which are the blind alleyways before we get to them. So I think these are the 2 things that I would push for. One is improving the theory, spending more time on the theory. We definitely need to improve the theory, but also finding new ways to accelerate the materials discovery by sharing our information more effectively than we're doing at the moment.
Yeah, one of the things of that spreading information was LK99 suddenly appearing in science, and everybody was captured by the news and tried to reproduce. But as an experimentalist, I have 2 just simple guidelines. So if it's low G material, I need to synthesize and pressurize it to whatever, see where a superconductivity appears. And if it's unconventional, I need to find the strange metallic state nearby, above liquid nitrogen temperature. So whatever unconventional superconductivity, strange metallic state will be hosting probably unconventional superconductivity that can go very high temperature. So at the moment, we apply various tools like pressure and field to find out basically unconventional metallic state. That's kind of guideline for me. But anyhow, let me switch our question to Yongju. You were desperately looking for a majorana fermion. And could you answer somehow simply finding out that, of course, intrinsic majorana fermion is useful for fundamental science, but do you have any expected application for that?
Well, thank you for your question about the majorana something. So actually, in the fundamental viewpoint, if we have the find the right way to generate the majorana stage and then control it, then we can find another way to develop a superconducting quantum circuit, which is topologically protected. But when I talk with the theoretical person, then whatever the experimentalist observed, any signature of the majorana zero mode, but they cannot believe it because the essential feature of the majorana zero mode is the braiding. So if I don't have any evidence of the braiding things using the majorana zero mode, then it is not majorana zero mode. But I'm working on the one-dimensional nanowire systems because it is clean and it is easy to manipulate, and then it is we are very familiar with the systems. But for the braiding, then in the one-dimensional system, it is not possible. So we need the extend the experimental system to the two-dimensional ones. But then I'm not sure whether we have the enough quality of the sample to provide that kind of the purpose. But if it is possible, then we can use the two-dimensional material platforms for the application of microenergy remote. Then it can open the another way. I mean, in addition to the topological computation, but such as the anion things. So it is the totally different particle states than the boson or fermions. So it will, in a fundamental physics way, then it will be very interesting. But the material issue is always there.
I see. So for topological quantum computer, also for Nobel Prize, I think this is good for future generation project, I think. And let me ask Sung-Yong. So you have shown very hopeful application directions and worldwide the current synergetic activity to build up this, to make use of high tissue wires and a high tissue magnet to make, for example, fusion program thing. And how do you think then this, we have discussed during lunch that the progress in China also is very huge recently. So how do you put our society, South Korean status in terms of high tissue magnet applications and also where we are?
Yes. Well,
compared with surrounding countries, for example.
okay, that's quite nasty question. I should be very careful. Well, you have to remember, again, 100 years, okay, that's a long time. And physicist has a dream of Nobel Prize if you be able to explain something critical. But think about the engineers that hourly word is actually quite practical. I'm not talking about the money. I'm talking about you can save human, you can make the life more efficient, right? So, but actually the challenge in HTS, particularly quantum protection, really disappointed a lot of people. Therefore, a number of engineers around the world is really small. Everybody included out count way less than 1,000 globally. That's the number. So it's pretty limited. Now, because of this new possibility, I'm not talking about no installation. I'm just talking about new possibility of engineering level of superconducting wire. Yes, no installation obviously opens a new delivers new philosophy and hope for magnet engineers. So yes, we definitely have a facing completely new era in applied superconductivity. So Korea, I mean, Dr. Coleman mentioned really good things because in Korea we have less than 100 people in applied superconductivity. I have to say, real experts. I'm not talking about graduate students. So with such a limited number and with a limited resource, the only way Korea to survive is to connect people and resources. So what we would like to do, we have one nationwide program, about $50 million for 5 years. And under this program, our target is let's use the same basis data whenever you design anything, for example, because people use all the different data. It's not comparable. Therefore, all the resources are wasted. I mean, results are wasted. So if you make the magnet and fail the magnet for some reason, let's get the record maintained and shared with the given data format. This is actually what we are working on right now here in Korea. This is the only way probably we can survive out of this competing area, this superconductivity. Compared with Korea, China, for example, I heard like a huge amount of budget devoted, and even industry responded very fastly, not to mention the US and the European people. So, but again, in Korea still we have a hope because this government is vigorously looking for a new technology. You probably remember last summer, LK-99, the desire of the community for the new opportunity, that obviously impacts our area. So right now, this particular government, although we have different stories, but actually try to support us quite strongly. Therefore, multiple meetings are waiting for us. So me and Professor Kim are about to answer those questions. What will be the direction of this country toward not only the theoretical or fundamental R&D, but the application. So coming back to his question, I think we are actually looking for a way to survive and connecting, sharing, and having a good data recording. And that, I think, are pretty essential steps. And I think we are probably one of the first countries pursuing this kind of combined strategy. So I, in person, believe the future of the applied superconductivity in Korea is not too bad. That is my answer.
Thank you for excellent answer for the nasty and intriguing question. So it's kind of time for getting the question from the audience. So if you have any question to specific scholars here, please ask. Yeah.
My name is Young-jo from Korea Basic Science Institute. First, I have many questions, but only time limits. I want to ask how can we use AI to search the material? In this industry, many companies use AI for the future, but in scientists doesn't use that. Is there any chance to use AI to search the highest superconducting material? That's my
One
question.
question. Do you have any other second question?
No.
Okay, so you can answer up here.
I can't answer this question, but I can give some reflections on it. You may know that, for example, in the area of protein folding, that the use of AI has completely transformed the scientific field. Used to be that to understand proteins, you would make a crystal, you'd make your Kriya from making that crystal, you'd then do an X-ray analysis, and you'd figure out the structure of the material. Now we're in a situation where you can more or less predict the structure of a protein once you know its sequence. Why? Because they had a huge database of protein structures that they could train the AI on. And with that huge database, the AI could figure out the rules and figure out the ways of predicting the structure. And so the field has transformed. And so what's the message you learn from this and similar achievements, for example, in playing Go? They could train the computers because they knew the rules, and they could then play the computers against each other and make themselves into great experts at playing Go in AlphaGo. But we can't really do that with strongly correlated materials today. We might be able to do it with weakly correlated materials. I mentioned lithium hydride batteries as an example. And so what do we need to help AI? We need to know the rules that govern the behavior. We need to be able to simulate things without using AI to start with. We also need much better databases on which to train the AI. AI isn't really intelligent. It's actually a pattern recognizing machine on a vast scale. And it can't recognize the patterns unless it can learn from the database. And so we need much better databases in materials physics. And if you look at the astronomers, they have these marvelous sky surveys. If you do a new astronomical survey, you put your data into the database, and it can be used by everybody. But when we have a failure at crystallizing a material in condensed matter physics, we don't enter it into a database. So nobody knows that particular combination of compounds doesn't really work under those conditions. And so I think one way forward, not only for the human researchers, but also for future applications of AI, is to have a much better database. And database doesn't only include the successes, it also includes the failures. You need to know what combinations of compounds don't work, as well as the combinations that do work. And so I think databases, and probably we need better theory to understand the underlying principles that govern highly entangled quantum states.
AI knows, I think, more than human. intelligent, and then can they develop the theoretical model or something like that?
So in the case of the protein folding, the humans have a basic understanding of the principles that are behind protein folding, but the detailed energetic structures are too hard for us to put into a simple theory, and that's where the AI has been successful. I think what you're suggesting is that AI might have some intrinsic intelligence, so that we might feed it all this stuff, and one day AI comes back to the human and says, well, I now understand the strange metal and high TC superconductivity. What would you like me to do for you? I think that's an unlikely scenario in the near future. This is not artificial intelligence. It is large language models. Okay, they are looking for patterns, and looking for patterns is part of intelligence, but it's not the only part of intelligence.
I hope you have answered for now your questions. And let's welcome another questions here. Any question?
So my question is actually from the Seung-Yong Han about the bright spark. Actually, I am a low temperature scientist now, so we generally want to higher field superconducting magnet. But in your development, it looks like reached higher than from 40 Tesla. But in the real experiment, is it possible to install that in the conventional dual or especially cryogen free?
I think you have two questions, I believe. If you answer the last question is, cryogen-free is quite common option nowadays. So I used to work in the National Magnet Lab, where I every day, daily basis, use the liquid helium. But then I returned back to Korea 2017. Then since 6 years, I never even touched the helium in my laboratory because every system is helium-free system. Okay. Now, if you're speaking of the 45 Tesla, whether that magnet is ready to go in HTS, unfortunately not, because the 45 Tesla small coil, after we reach the magnet at the field, the magnet turned out to be mechanically damaged. So the no-insulation magnet so far, there are one magnet right now, 18 Tesla, 70 millimeter diameter, axion detection magnet was installed back in 2017. And since then, 6 years, it has been continuously operated so far, even nowadays. I remember that's the only HTS magnet right now in the field, still operating. Other than that, yes, we have a National Magnetic Field Laboratory 28 Tesla magnet that's currently in maintenance for some reason. So to answer your question, we are vigorously working hard to make the HTS magnet feasible, but actually we're not that successful. Mostly the mechanical reason, we have a lot of failures. So now I have this chance to speak. I would like to answer Dr. Korman's very important question, whether theory or very strong understanding of HTS is important. I strongly believe so, because when we reached 45 Tesla with a small magnet, we have a very unique mechanical deformation pattern, damage pattern. Unfortunately, our community has failed to explain the why over the last 4 or 5 years. We really work hard because we do not understand how this damn current is flowing in this HTS conductor. Particularly, we call the screening current, or in your language, vortex current. There is a textbook equation that we are using. Unfortunately, it seems not working. So this is actually, I had a really hard time. So one day, Dr. Kim and I had a good discussion. So coming back to the question, unfortunately, HTS is not still unavailable. And therefore, your work, very hard work on the explanation on details, is quite critical for us to be successful in application.
Yeah. Do you have any other further question from the general participant? I heard. I see many new faces from the general public. Any question will be welcoming.
Thank you for the nice talk. I have one question to Dr. Seung-Yeon Kim. So you gave us several common features of the unconventional superconductivity, and one of things was the layered structure. But then, why do you think that the layered structure is very important to the emergence of the unconventional superconductivity?
Okay, so I think it's already actually the Jian actually already point out. There's quite. I mean that if you confine electron in the 2-dimensional or 1-dimensional actually environment, then actually you can actually boost up this a correlation and some fluctuations. So that means that you can actually increase the energy scale of this actually the exchange interaction. Then sometimes it can easily give us some interest phenomena at high enough temperature. So basically, low dimension is quite useful to enhance the fluctuation phenomena, which is quite important in a strongly correlated electron system. So I think there's even though I mean that you have to be careful. So even though the crystal structure itself is 3-dimensional, that 3-dimensional material can have a 2D-dimensional actually interaction. So it's not always actually attached to the structure itself. I mean that intrinsically, if you have a 2-dimensional interaction in a 3-dimensional material, then effectively you can also boost up the fluctuation as well. Yeah.
So you mean the important thing is the 2-dimensional correlation, and the layer structure can help those kind of correlation. Oh well.
Yes.
Thank you for your answer.
Yeah. Do you have any comment on also questions and answers in our speakers, or do you have any other questions? Last question. We hope we can finish at 5:30, and we have 10 minutes left, but we'll have some 5 minutes for wrapping up. So we'll be having now a last question, a 5-minute question.
코릴레이션 랭스를 생각해 보면은 원 디멘셔널 시스템에서는 더 늘어날 거라고 코릴레이션 랭스가 그걸 생각해 볼 수가 있는데, 사실 하이TC는 다 지금까지 발견된 건 다 어떻게 보면 레이어드 2D 스트럭처에서만 발견되었잖아요. 그런 것에 대해서는 어떤 이유가 2D에서는 높은 TC를 가지는데 1D에서는 안 가지는지에 대해서.
So his question was, his comment was that he's basically a graduate student, close to graduation, and he's an expert for HTC. But and now his question was that if you think about just correlation, 1D is the best in terms of low dimensionality, will be boosting up any kind of correlation or superconductivity. But so far, superconductivity in most of HTC is 2-dimensional. Is there anything special about 2D, not 1D? So that's your question, right?
I think it's quite harsh question. Okay. So So I would say that okay. If you only focus on superconductivity, maybe so you're right. Maybe it's a 2-dimensional. I think it's quite crucial. However, if you also actually consider other actually competing order, for instance, the high T superconductor, I think some people actually believe that it's a 1D actually charge density wave actually may be crucial for the high TC mechanism. So always it doesn't need to be actually 2D, but I think it's in 1-dimensional, you can actually induce additional another actually the emergent order, which can play as a glue for superconductivity. So because the superconductivity always appear in the vicinity of such kind of the emergent order. So in that sense, if you have a 1-dimensional charge density wave or then such kind of things, or vibrational mode in a 1-dimensional, that which may be helpful to actually to induce superconductivity. But I think Pierce may have a more actually solid answer. Okay, yes.
Did you turn on Michael?
Oh, okay, sorry. For the dimension is lower, its fluctuation is stronger. For 1-dimensional systems, it's very, very strong. Sometimes even long-range or long-range correlated superconducting state even cannot exist. So it's a balance. Yeah, it's a 2D system. Is fluctuation strong, but not as strong as the one-dimensional system. Furthermore, for the high TC layered superconductors, actually sometimes is kind of an interface effect, because you have a superconducting layer, but up the superconducting layer or nearby the layers, they can offers carriers or offers electrons for the superconducting state. But in the superconducting layer, maybe they can give you some strong correlation or some kind of a glue to make a Cooper pair. So this reservoir effect and the superconducting layer reservoir separate structure might be very important for high TC. Yeah. Okay, that's my supplementary content.
Can I follow up on that, on Jian's remark? So indeed, he's completely right that in one dimension, fluctuations are so strong that you can only in rare cases can you have long-range order in one dimension. Of course, that doesn't preclude the possibility. If you suppose you found a marvelous 1D system with very strong superconducting fluctuations, then what you would do is you try to link up those one-dimensional wires with cross-links. That would then stabilize the one-dimensional superconductivity as a two-dimensional system. The other aspect about 2D that's very important is, for example, it fits nicely with something like D-wave pairing. D-wave pairing works beautifully along cylinders of cylindrical Fermi surfaces, but it won't work so well on a spherical Fermi surface. And then just to end with a total speculation, one of the things you may know is that today's magnetism, first of all, is an amazing quantum phenomenon, and it develops at temperatures far above room temperature. Okay, so despite that fact, magnets from when I was a kid were nowhere near as strong as the magnets we now have today. Why is that? Because sometime in the 1980s, groups in North America and in Japan figured out that the main weakness of conventional magnetism is that the spins can point in any direction. They're Heisenberg magnets. And so by mixing in rare earth atoms, neodymium in particular, it was possible to make the first Ising ferromagnets, and it's the Ising ferromagnets that drive all of our magnetic systems today. It wouldn't be possible to have a high-powered electric vehicle without these marvelous Ising magnets that are central to the electric motors. And so one thought about this is that if we see pair fluctuations at 200 Kelvin, what do we need to do to slow down and condense those pair fluctuations? Maybe it's not a question of increasing TC, but maybe it's a question of reducing the fluctuations that destroy the coherence. And maybe there may be ways that we can find, who knows, that will, rather than raising TC, will somehow help the rigidity of the wave function. In the same way that we managed to make the rigidity of ferromagnets higher by using rare earth ions, is there something we could do to the structure that would make the superconducting state more rigid? And perhaps, as an example, that we're all trying to study a low-temperature superconductor called uranium ditelluride. And the reason we're trying to understand it is that even though it has 2 Kelvin transition temperature, it survives up to 80 or 70 Tesla. It has a very, very high upper critical field. We have no idea what stabilizes it, what makes it so rigid at high fields. And maybe understanding systems like this will help us answer the question of how to make superconductors more rigid so that they develop coherence at higher temperatures.
Yeah, please.
So connected with one-dimensional or two-dimensional, I mean, which which dimensional chance is more for finding new superconductors? Huh? So for one-dimensional, certainly the fluctuation is much stronger than two-dimensional normally. But in two-dimensional case, you have more chance for the superexchange. The magnetic superexchange channel, you have more. So you have J1, J2. So if it's only one-dimensional, then probably it's quite limited for this kind of magnetic superexchange. Okay, so in that case, two-dimensional could provide more chance for the magnetic induced pairing. Okay, concerning Piers mentioned that in the correlation induced superconductivity. So certainly if if the correlation is too strong, let's say half U is too large, then the chance for finding new superconductivity is less, because then the electrons cannot move anymore, and even the electrons, whether electron can be still regarded as the urea electrons, that's still a problem because it's too strong. So for exploring new superconductors based on the correlation picture, I agree with Piers that should be moderate correlation. So we need, at the one hand, we need the correlation to produce the magnetic, which induces the local pairing, and at the same time, we need these charge these electrons should be mobile. Okay, so we need this electron to move. Otherwise, we cannot establish the phase coherence. So it is a balance between the how to say the localization and itinerancy. So in the correlation system, we always we have always the balance of these two. Okay, so that's
Professor Wen, how about super lattice structures? Just use large U material, but other super lattices can offer the charge carriers. How about that?
That's a very good idea. Some series like Steve Kiverson says that using a super lattice or the interface, the heterostructure. Okay. So that can one layer provides a strong local pairing, and through the proximity effect to the neighbor, which has the higher superfluid density, higher charge carrier density. So in that case, weather can induce the high temperature superconductivity. I think it's a good idea. Yeah.
Okay, thank you.
Okay, so thanks for a great question and then the discussions. So as a final remark, actually he mentioned, Piers mentioned Ising superconductor, Ising model and the Heisenberg model, but with that concept of strongly having rigid superconductors, we have concept of development similar to Ising magnet. We also have Ising superconductivity. So interface or spin-orbit effect could help to have rigidity of a superconducting pairing state. One way to think about also another way is the pair density wave state that uranium-tellurium-2 might be also subject to that specific pair density wave state to pin the strong superconductivity to survive on the high field. So for the application point of view, increasing liberal field might be also useful to have this Ising superconductivity or a pair density wave competition. So that's my final kind of comment, if I'm not wrong. Okay, so
actually, there's one opinion that pair density wave state might be a mother state for high TC.
Right.
Okay.
Yeah. So that's kind of So we already have passed 5:30 as we promised, and probably it's time to wrap up. So let me just then conclude here. Okay. Yeah. All right. So let me just give you a final comment. So as you all can see from today's presentation, the study of quantum materials related to superconductivity and the future society that comes with it is now a very close reality. I hope that our society can lead the future scientific culture based on our understanding of this science and fulfill our role as a globally advanced nation in new industrial technologies and science. Thank you for your attention, and thank you for joining us for the BrainLink X Lab Day Talk Concert. Thank you.